Hi everyone. In a previous video, we talked about how to find the volume associated with a solid of revolution, and in this video, we're going to talk about how to find the surface area. So here's the situation we'd like to discuss. Imagine you had the graph of some function, such as the one you see here, and suppose you wanted to rotate that graph around some axis. In this case, we'll imagine a rotation around the x-axis. So take a moment to visualize the curve popping out of your screen and rotating, and try to think of what the resulting three-dimensional figure would look like. Hopefully, you were able to imagine the formation of something that might be described as a sideways barrel. When we rotate a curve around an axis like this, we've formed what's called a surface of revolution. And the big question we want to answer is, how do we calculate the surface area of this barrel, or more generally, of any other surface of revolution? Well, this should come as no surprise, but we could approach it by slicing our barrel into small pieces of surface area, which you might call DSA. And after that, you could add up, or in other words, integrate all the slices to get the total surface area, which we'll call SA. So the only remaining question would be, what's the best way to slice up our surface? Well, we can slice up the barrel by simply slicing up the curve that produced our barrel. And from our discussion of arc length, we're already familiar with the idea of slicing our curve into segments called ds, such as the one you see here. If you were to imagine rotating that one little segment, you can see the result would in fact be this ring-like slice of the barrel. So pause and take some time to visualize that rotation if necessary, and convince yourself that if you were to slice up the entire curve into segments, that would have the effect of slicing up the entire barrel into these rings. We would then need to ask ourselves how to calculate the surface area DSA of each of these rings. Well, for that, we would need the radius of the ring. And with the radius, we could calculate the circumference, which would be 2 pi r. Then if we multiplied the circumference by the width of that ring, which is ds, we would get the surface area. So this formula is another one I suggest adding to your formula sheet if you have one. Keep in mind also that the formula for ds was explored in the arc length video. So I'll provide it again here, but actually there were two formulas for ds. And you can choose between these two formulas based on whether you'd prefer to perform a dx integral or a dy integral. So make sure these two formulas are available on your formula sheet as well. Let's try putting these ideas into practice. Here we've been given a curve, which you'll notice is only defined on the interval from x equals 0 to x equals 2, according to the question. And the question asks us to rotate this curve around the x-axis and calculate the resulting surface area. The first thing I want you to do is make sure you can visualize this rotation. So pause if necessary and think about what the resulting three-dimensional surface would look like. I'm about to spoil it, so make sure you're ready. Hopefully, you were able to visualize the formation of what might be described as a sideways bowl, although the technical name for a surface like this is a paraboloid. Our task here is to find the surface area of this figure. And as suggested earlier, we're going to do that by slicing up our curve into segments. So I always start these problems by drawing a sample segment like this one and labeling it as ds. And convince yourself again that if you were to rotate that segment, you'd end up with this ring-like slice of our paraboloid. Let's use our formula for DSA to get the surface area of each of these ring-like slices. In order to do that, the very first thing I suggest is that you decide on which of our two formulas for ds you want to use. Technically, either of them will work, but it's important to make this decision early on so that we know whether we're trying to build a dx integral or a dy integral. So let's start by doing this as a dx integral with the formula I've just shown. I'll choose that one for now, and we'll see where that takes us. Aside from ds, our surface area formula also requires us to consider the radius r of this ring. And it's important that we express our radius in terms of the appropriate variable. Since we're doing a dx integral, we should get our radius in terms of x, not in terms of y. Notice that, like with volumes of revolution, the information we need can really be seen from the two-dimensional diagram without any need to ever actually draw the ring, provided you're able to visualize the rotation in your mind. So in this case, our radius can be seen as the distance from our arc length segment to the rotational axis, as you see in the diagram. And as always, we can find that by getting the coordinates of these 2 points. Let's start with the point at the top. Since we're forming a dx integral, we want these coordinates to be in terms of x. And using the formula for this curve, we can label that point as x comma root x. Now for this point at the bottom. This curve is on the x-axis, otherwise known as the line y equals 0, and so we can label that point as x comma 0. Since r is a vertical distance, we find it by subtracting the y-coordinates of these 2 points. And that gives us root x minus 0, which is just a fancy name for root x. Now we've got r expressed in terms of x, so we're done with step 2, and with that, we're ready to complete our formula for dSA. We've just found that 2 pi r is just another name for 2 pi root x, and for ds, we can sub in the formula we chose at the beginning. The part that I've left blank there represents dy over dx, but we don't know what that is yet, so we still need to calculate that by taking the derivative of our function. That's pretty straightforward though, just use the power rule in this case. Now insert this expression into our formula for dSA, and that completes step 3. Although you probably have an inclination to simplify a little, and there's no harm in doing that. So we've come up with this expression which represents the surface area of the slices. All that remains now is to add up those slices to get our total surface area, and that means integrate. More specifically, our total surface area SA will be the integral of all these pieces that we called dSA. But we still need to indicate our integration limits. Those, as always, indicate the position of our first and last slices, and we can look to the diagram to see that those are located at x equals 0 and x equals 2 respectively. So we'll use those as our limits, and we're ready to proceed. Once we plug in our formula for dSA, we're done setting up this integral, and all that remains is to calculate it. As you can see, arc length and surface area tend to produce some pretty challenging integrals just because of this square root. So I encourage you to pause here and try calculating this for yourself. There are multiple strategies that can work here, but one strategy you can use is this. First, notice that x to the minus 1 can be expressed as 1 over x. And in the video on arc length, I suggested that when you're working under a square root, it can be a good idea to form a common denominator. So let's go ahead and try that, which would provide us with this result. The real advantage of doing that is that we can now distribute the square root, or in other words, we can apply it separately to the top and bottom of our fraction. So first, let's apply that square root to the top. And when we apply it to the bottom, we'll end up with 2 root x. Once you've done that, you're going to see that quite a few things can now be canceled out. And after that, we're actually left with a much easier integral. So what should we do next? Well, observe that the square root contains an expression whose derivative is just a constant. So that would make for a pretty easy u substitution, since the calculation of du wouldn't cause any complications for us. So the rest is pretty straightforward. So pause here and check that all these remaining details provide us with a final answer of 13 pi over 3 square units of surface area. If we go back to the very start of the problem, it's possible that we could have done this differently by choosing to build a dy integral using this formula for ds instead. So for good measure, let's think about what that would have looked like, just to get some more practice with that approach as well. So the major difference would be that when we go to calculate our radius, we would want it in terms of y rather than x. So when we go to look at this point on our curve, we're going to say that y in terms of y is just y, and for x in terms of y, we'll rearrange the formula for our function to see that x is y squared. As a vertical distance, our radius will still be computed by subtracting y coordinates. And we just found that the y coordinate at the top is just y, and at the bottom, we know the y coordinate is going to be 0. So with a bit of simplification, we have our formula for r, y minus 0 is just y. With that, we're ready to complete our formula for dSA just like before. So we just saw that r is equal to y, and the formula for ds was decided at the beginning. But we still need to fill in the blank part by calculating dx over dy. So for that, we take the formula for our curve, and we need to rearrange it so that y is the independent variable. So that's pretty easy to do in this case, but then we can just apply the power rule to get this derivative as dx over dy, and include that in our surface area formula. After a bit of simplification, we've now completed our formula for dSA. Now that we know the surface area of all the slices, the last thing to do is add them up, and that is done by integrating. But we still need to figure out our integration limits. For our dy integral, those should be values of y, so just keep that in mind. As always, we look to our diagram for our first and last arc length slices, but we identify their positions by their y values. Of course, that can be done by plugging in the corresponding x values into the function. That would show us that our integration limits would be y equals 0 and y equals √2 respectively, and the only thing left to do now is calculate this integral. Pause and think about how to do that, and when you're ready, let's look at the correct method. The key to solving this one is to look at the inside part of the square root and notice that the derivative of that inside part looks very similar to the factor of y that we see in the front. And when you notice that pattern, when there's something inside whose derivative appears as a factor, that's a good indication that a u substitution will do the job. And sure enough, you can check that the details of that substitution do work out pretty nicely and provide us with a final answer of 13 pi over 3 square units, just like we got before. That's it for the basics of surface area, so I'll end the video here and see you next time.